We start with a small topic called Maxima and Minima, which is applications of derivatives. So we see the applications of maxima and minima to word problems. Let D be a subset of R and F be a real valued function defined on D. A point C in D is called a stationary point or a critical point or a turning point of F if two conditions are satisfied. First condition, F is differentiable at C and F dash C equal to 0. And second condition, if F double dash C, that is second order derivative of F at C equal to 0 and third order derivative of F at C is not equal to 0, then C is called a point of inflection or a saddle point. I repeat once more, C is called a stationary point if the first order derivative of F at C equal to 0. If the first order derivative and the second order derivative of F at C equal to 0, but the third order derivative of F at C is not equal to 0, then C is called a saddle point. Based on this, we have the second derivative test, which is very useful in word problems on applications of derivatives. It states that if F is a real valued function such that first order derivative of F at C equal to 0 and second order derivative of F at C is greater than 0, then F has a local minima at C. Further, if first order derivative of F at C equal to 0 and second order derivative of F at C is less than 0, then F has a local maxima. I repeat, for second derivative test, the first order derivative of F at C has to be equal to 0 in both cases. If the second order derivative of F at C is greater than 0, then F has a local minima at C. And if the second order derivative of F at C is less than 0, then F has a local maxima at C. So you can see the figure. There is a local maximum here, local minimum here. The word local means it is only at this point, around this point. Again a local maxima here because the graph comes up and goes down. So at this point it is maximum. And here you can see that it is neither maximum nor minimum. So this is called a saddle point. Coming to problems, a box is to be constructed from a square metal sheet of side 60 centimeters by cutting out identical squares from the four corners and turning up the sides. So you have a metal sheet of side square metal sheet of side 60 centimeters. You cut out identical squares from the four sides and fold up the sides. Find the length of the side of the square to be cut so that the box has maximum volume. So we are cutting out x from each side. So the length of this side would be 60 minus 2x. The same would apply for all the four sides. So volume is length into breadth into height. That would be, this is 60 minus 2x, 60 minus 2x and the height is x. So volume would be 60 minus 2x the whole squared into x. Take out 2, so it is 2 into 30 minus x the whole squared into x. That is 4x into, when you square 30 minus x the whole squared, a minus b the whole squared, a squared minus 2ab plus b squared, 900 minus 60x plus x squared. So multiply by x, you get 4 into 900x minus 60x squared plus x cubed. Now take the first order derivative, that would be 4 into derivative of 900x is 900, derivative of x squared is 2x and derivative of x cubed is 3x squared. So I get 4 into 900 minus 120x plus 3x squared. To use the second derivative test, equate dv by dx to 0. So you get 4 into 900 minus 120x plus 3x squared equal to 0. Divide by 4, you get 3x squared minus 120x plus 900 equal to 0. I am just rearranging the terms here. Take out the 3, you get 3 into x squared minus 40x plus 300 equal to 0. You can factorize x squared minus 40x plus 300 to x minus 30 into x minus 10. So we get 3 into x minus 30 into x minus 10 equal to 0. So there are two possibilities, either x is 10 or x is 30. Now if x is 30, you cannot cut out a side of, from the side of side 60, you cannot cut out 30 from both sides. So x equal to 30 is not possible. Now calculate d2v by dx squared, the second order derivative. dv by dx is 4 into 900 minus 120x plus 3x squared. So if I take the second order derivative of this, derivative of 900 is 0. Derivative of minus 120x is minus 120. Derivative of 3x squared is 6x. So we get d2v by dx squared will be 4 into minus 120 plus 6x. That would be minus 480 plus 24x when you multiply by 4. So when you substitute d2v by dx squared at x equal to 10, you get minus 480 plus 24 into 10. That would give you minus 480 plus 240, which is less than 0. So volume is maximum when x is 10 centimeters by second derivative test. So length of the side cut out is 10 centimeters. That answers the problem, which says that the length of the side of the square to be cut out so that the box has maximum volume would be 10 centimeters. Going to the next problem. A rectangle is given whose area is constant. Prove that the sum of the lengths of the sides is least when it is a square. By sum of the lengths of the sides, I mean a perimeter. So if this is the length, area of a rectangle is length into breadth. So breadth would be a by x. Now perimeter is 2x plus 2a by x. So taking the derivative of p with respect to x, you get 2 minus derivative of 1 by x is minus 1 by x squared. So we get 2 minus 2a by x squared. Equating dp by dx to 0, you get 2 minus 2a by x squared equal to 0. So the 2 gets cancelled and you get a equal to x squared. Now d2p by dx squared, the second order derivative would be derivative of x squared x raised to minus 2 is minus 2 x raised to minus 3. So this would give you 4a by x cubed, which is greater than 0 whatever be your value of x. So the perimeter is minimum when a equal to x cubed because second order derivative is greater than 0 and x is positive. A equal to x squared means the breadth is also x. So the given rectangle is a square. Next problem. Prove that the perimeter of a right angle triangle of given hypotenuse is maximum when the triangle is isosceles. So we have a right angle triangle here. Now cos theta is adjacent side by h. So adjacent side will be h cos theta. Sin theta is opposite side by h. So opposite side is h sin theta. Now if p denotes the perimeter, p will be h sin theta plus h cos theta plus h. That is, take out the h in the first two terms, you get h into sin theta plus cos theta plus h. Taking the derivative with respect to theta, because h is the hypotenuse which is constant, derivative of h becomes 0. So derivative of sin theta is cos theta, derivative of cos theta is minus sin theta. So dp by d theta becomes h into cos theta minus sin theta. Equating dp by d theta to 0, you get h into cos theta minus sin theta is 0. That means cos theta equal to sin theta, or dividing by cos theta you get tan theta equal to 1. Tan theta equal to 1 means theta is pi by 4. Now take second order derivative d2p by d theta squared. Derivative of cos theta is minus sin theta, derivative of sin theta is cos theta. So d2p by d theta squared becomes minus h sin theta minus h cos theta. That is minus h into sin theta plus cos theta, and since theta is an acute angle, sin theta cos theta is positive. So second order derivative of p, that is d2p by d theta squared, is less than 0. So by second derivative test, perimeter is maximum when the triangle is isosceles. Thank you for listening to the video. In case you need any help in any topic in ICSE, ISC or CBSE Maths classes 10, 11, 12, you can contact me on matthews.suman@gmail.com. Thank you.